I want to finish up where we were on whenever it was.
Oh yeah, without proofs.
With finishing the contraction mapping principle. So where I was, I believe, at the end of Monday was we had the sneaky proof that if you have a sequence of real numbers, not vectors, just real numbers, a sequence of real numbers with the sum of the absolute values converging as an infinite series, then the series itself must converge. Remember what the word was?
Absolutely convergent.
Absolute convergence, right. So absolute convergence implies regular convergence for sequences of real numbers, a series of real numbers. And the application is going to be if you have a sequence of vectors now. So now you know why I'm using k for my sequence and not n that you guys were used to for calculus, because we're in Rn. So if you have a sequence of vectors in Rn, and the series of their magnitudes converges, then the series of vectors actually converges. How would you prove that?
Comparison.
Comparison of what?
Never mind. That one. Yeah. Well, AK is always going to be greater than the magnitude of AK is going to be greater than.
You're like contrary positive.
Well,
I mean, I want to reduce to the single variable case that we've already proved.
Well, we know that each
Say
coordinate
if.
converges. Just go coordinate by coordinate, and if you prove that each coordinate converges to a point, then the sum of the vectors converges.
So again, I'm going to remark that those of you who know the word Cauchy,
Well, can you have AK be switch off between like the standard basis vectors?
say what?
Can you have AK be a sequence that just rattles through the
This is,
Then that would converge.
remember, this is an infinite sequence. You have this for all k from 1 to infinity.
yeah. And so like
But these have to go to 0. If you have a convergent series when you take their magnitudes,
okay,
these have to
yeah,
approach
yeah.
0 in particular.
Okay.
But you could look at the sequence of partial sums of these vectors. This is what you always do, and those of you who will still take 3100 will play with this more. You will always work with sequences of partial sums. You could show that this sequence of vectors that you get by adding a part of the series is a Cauchy sequence of vectors. And Cauchy sequences converge. So if you know what that means officially from either 2410 or 3100, you can do the proof that way. And this works, as I said the other day, even in infinite dimensions. But since we're not going to use that in this course, I'm just going to do the proof that Yumeng and Daniel were suggesting. All we need to do is show that for each component, so you have n components to your vectors, take the ith component of the vector AK. So AK as a vector, I'm writing as AK, comma 1, AK, comma 2, up to AK, comma n. So take the ith component of the vector AK and show that the sum of the ith components converges for every I. And then we'll know that the series converges as a vector. Fair enough? remember we just talked about when we were doing sequences in chapter 2, we talked about how you can detect convergence of a sequence of vectors component by component if you wanted to. So this is the same thing for the series. Well, so what do I know about?
Well, you know that a bigger sum converges already with some magnitudes.
How do I compare the magnitude to that?
It's greater than or equal to that.
So we know that the absolute value of the ith coordinate is at most the length of the whole vector. We know this series converges, so by comparison, this series converges. So the absolute values of the ith coordinates all gives you a convergent series. So by what we proved, the series without the absolute value signs converges. And so we're done. Everybody okay with that? So the key thing is that knowing that the lengths of the vectors when you something convergent means that component by component you're convergent. All right, so now we need to use this to finish the proof of the theorem. So here we have this result, and I want to apply it. So, proof of contraction mapping. So what did it say again? It said we had some function that was a contraction mapping.
Had a unique fixed point.
Then we're supposed to show it has a unique fixed point. And somehow out of this function, I'm going to create a sequence of vectors and try to prove a sequence converges through this shenanigan. It's all very contrived, or convoluted is a better word. I mean, but it all works very elegantly. So choose any point x0 in your set X and iterate the contraction mapping. So let x sub k be f of x sub k minus 1. K going from 1 to and so on. So I start with x0. So here's my set X. I start with x0. I apply f to it. And then I have x1. Now I apply f again. Could it end up way over here?
No, it has to be closer. It has to be closer.
Closer to whom than whom?
Closer to
Closer to the
x2 than x0.
Closer to x1 than x1 is to x0.
There you go. So exactly right. This distance has to shrink by a factor of c or more. That's what contraction mapping said. Right? So remember we said f of x minus f of y in magnitude is at most c times the difference between x and y in magnitude. So whatever distance this is, the distance to x2 is less than or equal to c times that original one.
It has to. That has to happen.
Well, does it not have to happen?
It does have to happen. But then we should-
Well,
Why not, Jonathan?
well, like kind of what we've done better at the homework. Like, let's say the lengths are getting like bigger and bigger, and it's approaching like.
No, but we're given this. So if I plug in x1 and x0, then I get f of x1 minus f of x0. Well, that's x2 minus x1. The magnitude is at most c times the original distance. So this distance is less than or equal to c times that distance.
Okay.
If I do it again to get to x3, what do I know? Well, this distance is at most c times that distance. So these guys can be zigzagging all over the place, but what has to be happening?
They have to be closer and closer together.
They have to be bunching up more and more.
And as k goes to infinity, it goes to 0. And that's why.
So we're going. What do we want to claim about this sequence of xk's? You have to claim it, you want to claim it's converging. So the claim is going to be that xk's, that sequence converges to some point A. Maybe I won't call it A, just because of the other A's. Let's say Q. All right, so the key observation is that if I take the distance between xk plus 1 and xk, it's at most c times the distance between xk and xk minus 1. I'm just writing down what we were saying. And then what's that less than or equal to?
C squared.
Times?
X of k plus 1
No.
or
Go backwards.
x of k minus 1
minus x.
Right? Each time you pull out, you say this is f of the previous one, this is f of the previous one, so that you pick up another c, and then you get xk minus 1 minus xk minus 2.
Can you go ahead and use epsilon in there?
I'm not, no epsilons. But you can keep going until eventually you get back down to, what's the final,
Yeah, x.
x1 minus x2.
just the original x1 minus x0 distance, right? The original distance here. Now what power of c do I end up with?
Or ck plus 1.
I don't know. It's c to the something.
K.
CK.
You main votes k. Anybody?
You left a lot of skips.
K.
Well, I wasn't sure.
Yeah, I'd say K.
It's k.
So the way to convince yourself, you can do an official proof by induction, but the way to convince yourself is to try it out for small k's. Because you know there's a power here that has to work, because you've iterated this a certain number of times, and all we care about is how many times. So suppose k were 1. What would I have here?
C.
2 minus 1. And then it should be c to the 1. So if it's k plus something and it works with k when k is 1, it has to be c to the k. So I left too much space. So this is true for all natural numbers k. Agreed? So this prompts me to consider not the x's, but these vectors that are differences of x's. So in other words, I want to now think about this vector as a1, and this vector as a2, and this vector as a3, and so on. And then I want to apply our...
How'd they know?
Your birthday, Jonathan?
Mine's in April.
It's not Llama's birthday either.
No.
I don't know whose birthday it is.
I know you're talking about that.
So set ak equal to x sub k minus x sub k minus 1. So if you look at the differences between successive x's, call that a sub k. Then what we've argued now, that the magnitude of ak is less than or equal to what? Just rewrite that thing we just did.
C to the k, x1 minus x0.
Well, what's x1 minus x0? It's a sub 1, isn't it? Right?
Maybe AK plus 1.
Oh, do I have an index wrong? Yeah, this is k plus 1. Thank you. Yeah, exactly right. What does this remind you of? Some number at most c to the k times a fixed number. Suppose you didn't have the at most, but you had equals. What would that remind you of? Not something we just talked about, but something that's showing up in your homework.
A limit, I mean, take the limit as k increases.
Well, that goes to 0, but what do you know about,
Geometry series.
yes, geometric series.
Oh.
Consider the series now of the magnitudes of the AKs.
Right, this does show.
Does this series converge?
Yes.
Well,
Because
you
K-
compare it to a geometric series here. Right? Each one of these terms is bounded by c to the something times a fixed number. So that means if I do the infinite series, I'm comparing it, I'm saying it's bounded above by the geometric series of the c's, the powers of c, times the fixed number of magnitude a1. This converges because
C is less than
c is less than 1. Here's where you explicitly use c is less than 1. So this converges because c is explicitly less than 1.
So that's less than C.
Yeah, so you actually can write down the sum, and in fact, you can give it, because you have a formula for the partial sums of the geometric series, you can give a bound on exactly what the sum to the first number is bounded by. But what we know is, by comparison, this series converges. Therefore, what series converges? The series of a sub k's with no bars on them. So by our application in orange up there, the sum of the vectors themselves converges.
Would it be c to the k plus 1?
Or minus 1?
Or yeah.
Yeah, it is, but it's still re-index it. So what is the sum of a sub k's converging to? Well, it's converging to some vector that corresponds to adding up all those red arrows. Now, A1 had its tail at x0, not at the origin, the way I've drawn it. So what do you get if you take A1 plus A2 plus up to AK? You get
x1 minus x2.
close.
X k
No.
minus x naught.
You get x1 minus x0 plus x2 minus x1 plus up to x k minus xk minus 1. So what does this whole thing do?
X k minus x naught.
Telescopes.
It's what's called a telescoping series, if you remember that from your calculus days. And everything cancels but the first term or the zeroth term and the last term. So if this series is converging to somebody, its limit is telling me if I add what it converges to x0, I get where xk is. That's sort of obvious from the picture. So if this converges, if this infinite series, say, to vector A, this converges to A, so if I add x0, I'm getting what the xk's converge to, namely A plus x0, which is exactly what you would say. You go to x0, and then you start your zigzag route, and it takes you to the limit of that series. And that's going to be your limit of your x's. So that's the proof. What's nice about this proof is that because of the geometric series here, you actually get bounds, very effective bounds, on how quickly it's converging. Right? So you can get an estimate on how far xk is from the limit by just looking at how far, forget the x naughts, look at how far the sum of the a's is from the limit. Yes, sir?
Okay, so the series over there, is it geometric, arithmetic?
Whoa, say again?
The series there.
This?
Well, okay, so the first one on the left is geometric or arithmetic?
Neither. This?
Yeah.
It's neither, but you know it's bounded by a geometric series.
I'm just confused. Are you adding up all the terms or multiplying all the terms?
Adding.
Okay. Cool.
Geometric series is still a sum when you add up powers of a fixed number times the powers of a fixed number.
If it was,
Okay.
it'd be like
Sorry.
pi, like you're multiplying it together.
Yeah, we're not multiplying.
Okay.
So you can estimate how far xk is from the limit by saying that's the same thing as how far the sum of the a's is from the limit. Right, this is the partial sum of the a's, a1 to ak, minus the limit. And that is the tail of this series, where you go from k plus 1 to infinity. And so by the triangle inequality, this is at most the sum of the magnitudes, looking at the tail of the series. And so you're now taking the fixed A1 vector times this geometric factor. What do we know? Magnitude of AI is at most c to the I minus 1, I going from k plus 1 to infinity. So in other words, if you know how to bound the tail of a geometric series, you know how quickly your x's are converging to q. And so you guys remember how you do this? This is the same as re-indexing. If I starts at k plus 1, what does I minus 1 start at?
Okay.
Okay. So this is, we're just saying, what do you get if you add up the powers of c starting at c to the k? Remember doing this in high school or in Calc 2?
Can you just multiply by c to the whole thing with c to the k?
Right, at ck, you can pull out a c to the k, and then what you're left with is the whole geometric series. Which you know converges to 1 over 1 minus c. So you actually have a bound, and you see roughly that the rate at which this convergence is occurring is by powers of c. And that goes to 0 very quickly. If you fix a number less than 1 and take its powers, that converges very quickly to 0. Yes, Gabe?
Sorry, when we go back to the note, how do we get that, the summation from I equals 1 to k, ai minus a equals?
Because a is the limit. So a is the infinite sum from 1 to infinity, and if I take out the first k terms, I'm left with the tail.
So if we prove that the fixed point, that the point it converges to is fixed, we've proved that?
That's from homework from last semester. If you have a sequence made by iterating, and f is continuous, then the limit, if it exists, is a fixed point.
Okay.
So that was number 9 in section 2.3.
And we showed that AK converges, that means that last AK equals 0, right?
Well, there is no last one, it's infinite, right?
Right, but
in the limit, they're
there-
going to 0, and
Right,
there's
so the last whatever the infinite one would be 0, and that's xk minus 1, so it means it has to be fixed at the end. Because they have to go 0.
I mean, if there were a number called infinity, and there were a last term that you would call a sub infinity, you could say that, but it's not literally true, it's a limit statement.
Yeah.
Is there another question? Yeah, so Daniel's recall, I said this to you guys last class, that the fact that Q is a fixed point follows from homework. So, appendix. Contraction mappings are continuous, because you just did that in homework. So the limit of x sub k, which we said is q, is the limit of f of x sub k minus 1. That's by definition, right? The way you get xk is by iterating f. But by continuity, what happens when you take f of a sequence if you have a continuous function? It approaches f of the limit. Well, the limit of that sequence is also q, right? If a sequence converges to q, so does the sequence you get by doing it one back. It also goes to q. So that's why it's a fixed point. Other questions?
That's only if we know k minus 1, right? That's only if we know that k minus 1 is in the set. Like you started at x naught, you could like
We're doing the limit as k goes to infinity. All right. So I was going to make a comment since we discussed Newton's method briefly, and some of you told me you've actually never really seen it, so I want to talk about it for a few minutes. We're doing problem 8, which explores Newton's method in quite some detail, but a few comments on Newton's method. So remember we had this picture that you had some differentiable function g, and you're looking at its graph and you're trying to find a root, and what we said is you start at an arbitrary point x naught and you look at the tangent line to the graph at that point on the graph, and you define x1 by seeing where that tangent line intersects the x-axis. You then iterate that procedure. So this would get you a new tangent line and a new point x sub 2. And so what we're doing is exactly this iteration scheme where you start with an x naught and you create a new x. And I'm doing this just for real value functions, although problem 10 talks about vector value functions with Newton's method, with vector variables. So what's the function we're iterating? Well, so let me just remind you, I said on Monday how this comes about, but since some of you have never seen this, let's quickly do it. Here you are at a point, let's say you're at a point x naught, and you draw the tangent line, poorly. Okay, what's the equation of the tangent line?
F of x.
So y equals slope. Well, what's the slope? If it's the tangent line at x naught, it's g prime of x naught.
times x naught. prime plus y naught.
So that's, right, point slope formula would be y minus y value, which is g of x naught, equals slope times x minus x naught.
Is
Agreed?
it,
What we want for the tangent line is where it crosses the x-axis, so we want the x-intercept. How do you find the x-intercept?
so y?
Say y equals 0. And when that happens, we're calling that point x1. So we're solving for x1. So we're taking negative,
Yeah.
well, let's see.
Negative g of x divided by g prime.
All right. I
We'll
bet.
just add x.
So negative g of x naught equals g prime of x naught times x1 minus x naught. Divide by g prime of x naught. And then add x naught. So there's the function you're iterating to make this method work. So now what you've noticed from the proof of the contraction mapping principle is we said that the convergence rate here is basically geometric. That if you start at a certain distance apart and you have a contraction rate of c, that you get at least c closer to the limit every time. That's very fast convergence.
Could you have like a quadratic Newton's method if you were feeling like it?
Yeah, the algebra is more trouble than it's worth.
I bet, yeah. I was just curious.
Yeah, how much
The problem is,
You'd have multiple.
well, you might, yeah, I mean, what would you look for? If I took the approximating parabola here, it wouldn't even have an x-intercept.
Well, no, it could be other.
That's not the best fit. So if you tried to approximate by Taylor polynomials of degree 2, you would be approximating by the best fit parabola here, which would look something like that. And then what do I do with it?
Yeah, okay.
Nothing.
All right, so so the question comes up then naturally, and this is partly to answer David, who wanted to know what was going on in number 8. Nice erasing chalk there. Is F a contraction map? Well,
Better hope so.
what did we talk about on Monday? Because of the mean value theorem, it's natural to look at the derivative and see what the derivative looks like. And if the derivative has absolute value less than some number c, less than 1, then you know you've got a contraction map. So what is f? Let's compute f prime. All right, folks. Do it. Dictate.
One minus
You got the hard part. Now do the easy part.
g prime
lower,
squared.
yeah,
In the denominator, maybe?
no, in the,
in
both
the
the
numerator.
denominator and the
G
denominator.
double prime.
It's Lodi high,
Oh,
so
G
g
prime
prime,
squared.
g prime, minus g double prime over g prime squared.
Is that correct?
Yep.
So what do you notice happens?
You get one,
You get, the
One.
one goes away.
The
Yeah.
1 cancels
you
this.
just get negative at g prime.
Negative, negative.
It's positive, yeah.
So if you were trying to control the derivative of f, you would want to have upper bounds on g and g double prime, and you'd want a lower bound on g prime. You don't want g prime getting too close to 0, because then that makes the reciprocal blow up. So naturally want g bounded by something, G double prime bounded above by something, and then the derivative bounded below by somebody that's strictly positive. And then what you hope happens if you want to have a contraction mapping you hope that if you take the absolute value of this,
It'll be less than or equal to C less than 1.
right, so the biggest the numerator can be is m1 times m2, right, because you have upper bounds on G and G prime. And the smallest you could have in the denominator would be little m squared. And you hope that that's less than or equal to C on an appropriate interval.
This looks like a physics, like a gravity problem.
Well, it's a balancing act among the function its second derivative and its first derivative. So, in case you're wondering about what's going on in the hypotheses of number 8 that you're all working on or have finished working on, it's very much in this sort of framework. And I'm actually going to give you some numbers for an example.
Could they not be bounded and like cancel each other out?
Huh?
Like,
You say what if like g of x got really big, but g prime of x also got really big, and they sort of nulled each other?
Remember, you're trying to find a root of G, so you're trying to stay near where G is 0. Right? You're trying to hunt for a root of G. So this is pretty natural that you don't want G being big. You want it to be relatively small. If the second derivative went off to infinity, the first derivative also went off to infinity, I suppose that could happen. But you're working on some closed interval, so there are constants by continuity in maximum value theorem. Right? You're trying to, so you want to be on a relatively small interval in order for this to work. And so, remember I mentioned trying to find where cosine x equals x. And this is actually, I believe these numbers are in the book. But if you actually look at this bound here for f prime. So start on the interval when x is between 0 and pi over 3. Well, if I graph f prime, here's what it looks like. I'll actually write down the formula for you. F prime.
You mean g prime?
No, I mean f prime.
Oh yeah.
You actually do this to do iterating Newton's method. To find the roots of this function, you actually get x minus cosine x times cosine x over 1 plus sine x squared. And it actually starts off at 0 at -1. And increases like this. So this is bad, right? Because the magnitude of f prime is 1 if you include 0. So you don't want to apply Newton's method starting at 0 with that function. You want to stay away from 0. And in fact, my picture here is off. But if I actually took pi over 6 here and looked at this interval from pi over 6 to pi over 3, then you would be relatively small, and in fact, absolute value of f prime is less than 0.0132, which is definitely less than 1. So that would be your C that would work for sure. And so you can see that if you start at a reasonable place, not too far from where G is finding a root, this is the graph of f prime here, then, great. I don't like that. Oh yeah, okay, that's f prime, not g. So f prime will have a root. F prime will be 0 when you're at a root of g. Right? When g equals 0, f prime is 0. So this place where f prime crosses 0 is also where g is having the root we're looking for. And as long as you're staying away from starting at 0, you can see it's going to converge very quickly because you're taking powers of a number that's approximately a tenth. So the convergence is extremely rapid.
So what would happen if we tried to iterate f starting with x not being 0? I mean,
So let's see.
It wouldn't contract, but
So x minus, this is where I wish I could just fire up Mathematica quickly. X minus cosine, so we're doing negative, oh, no, that's terrible. So if you're starting with x minus cosine x at 0, it looks like cosine minus cosine x.
right.
So you get it
Then you multiply it times 0.
X minus that, so it's, no, but it's headed up at slope 1. So
What are we graphing here?
I'm trying to graph g, because we're doing Newton's method to this.
Right. It looks sort of like a staircase,
Yeah.
like a curvy staircase.
Well, I guess I'm not starting the next chapter though.
Well, we can, this is not really important, so. We can do it in office hours if you
Yeah, so it's just, it actually looks like this. This has slope 1 here, right? Because the derivative of this at 0 is 1 minus 0. So if you started Newton's method at 0, it would start off with a slope 1 line that went like that. So you're right, it's not literally a contraction where you started, but then it's converging pretty fast again. So even if you started at 0, the theory doesn't give you an effective bound because of the starting point, but once you get off that starting point, you're fine.
Okay.
Other questions?
Choose about choosing an interval on, I guess, the last problem, 9b. It talks about choosing an interval. What it like? So.
No. Well, apply what you learned in number 8.
Okay.
It gives you the right interval.
Okay.
So on my TI-89, when I want to find the x-intercept of a function, I choose an interval. Is it just applying Newton's method on that interval?
Yeah, it should be. Yeah. You choose an interval or you choose a starting point?
I choose an interval.
Yeah, it says click on basically.
You click to the
internal
left and to
side
the right.
before you know that
I
there's.
wonder if it's then doing some sort of,
It's a double.
I wonder if it's doing successive bisection then, and just cutting in half each time, and I don't know, actually, what. I'd be surprised if you're picking an interval that then it's doing Newton's method.
It's probably bisection because you have to include the root in your interval.
Yes. But I'm wondering why it's doing an interval. If it were only doing Newton's method, it would only want you to start somewhere.
Right.
So I'm guessing it's comparing f at the endpoints, cutting it in half, comparing f on the endpoints, cutting it in half. That's what I'm guessing it's doing. Okay, so quick introduction to where we proceed tomorrow. So the point of our doing this contraction mapping, aside from you're getting to play with a really neat, powerful idea that shows up lots of places in applications, is we actually want to find inverse functions for functions by applying this contraction mapping idea. So our goal for the next couple of days is going to be to use contraction mapping to find, in quotes, inverse functions of C1 functions. So just to show you why the C1 is needed, let me pose a question for you to ponder briefly. Question. Suppose f is differentiable and suppose the derivative at some point is positive. The question is f increasing on an interval around A? So here I'm just doing real valued functions of a real variable, no vectors. So go back to Calc 1. Think to yourself, I'm headed uphill. Am I increasing nearby?
Yeah.
Who's continuous?
I feel like
This is like the problem. This is like the problem where if a function is positive somewhere on, it has to be positive on an interval.
Well, that's assuming
That's
the
when
derivative
it's
is continuous.
We need the derivative is continuous.
And I know that we found examples.
Listen to that man. He knows where he speaks.
So that hence C1.
So, I did not say C1 here. I said f is differentiable. Is it true that if you're headed uphill, then you're an increasing function nearby?
We could have like a step.
Hmm?
We could have like a step.
It's differentiable.
Well, I'm saying that, I'm putting it in real terms. Never mind.
Apparently not.
So you guys may remember,
It's really
you could imagine having a function that was headed uphill at 0, but so that the derivative did not have a limit as you approached here, and the derivative wobbled up and down, so it went from positive to negative even as you approached that point. So, do you recall a function from last semester where we took this?
Where it's sine 1 over x.
And you will recall that that was an example of a function that was differentiable everywhere, but its derivative was not continuous. Because as you got closer and closer to here,
This was the answer to one of the exam problems, right?
probably,
Definitely didn't get this one.
as you got closer to here, the derivative is oscillating back from -1 to 1, faster and faster as you come in. So what I'm going to do, and you can see a picture in the book, and we'll start with this tomorrow, quickly, tilt it. Take this picture and add half x to it. So it's heading uphill with slope a half. Well, if you take, if this piece had derivatives that were very close to -1, and you add a half to -1, it's -1/2, which means arbitrarily close to the origin, when you tilt this thing, it's still got negative derivatives arbitrarily close, which means it can't be headed uphill. So, as unintuitive as this is, the answer to this question is no. So this is why we're going to talk about C1 and why that's important. Okay, so reminder, new homework assignment is here. I will collect the current assignment Monday, and I will collect Thursday when we meet our special time.